स्वागत है आप सभी का फिर से यूट्यूब चैनल में, जहां पे आज हम देखने वाले हैं कंट्रोल सिस्टम प्रैक्टिकल रिगार्डिंग रूट लोकस. So outline of this particular practical is: first we discuss root locus, then poles and zeros, then root locus construction, example to be solved using scilab. So poles and zeros. So this is the basics of poles and zeros. Here f of s is a function that given k s minus z1, s minus z2, s minus zm is indicated by zeros, s minus p1, s minus p2 indicated by poles, and this is the imaginary axis and this is the real axis. Pole indicated by cross sign and zero indicated by circle sign. Root locus. So this is the basic block diagram with the feedback of h of s. K is a gain and g of is a open loop transfer function. So T of s, that is equal to y of s divided by r of s, that is equal to k into g s divided by 1 plus, because here negative feedback is there, that's why 1 plus k into g of s h of s. So we will start finding a root locus with the help of characteristic equation, that is equal to 1 plus k g of s h of s, that is equal to 0. That gives poles. Now 1 plus k g of s is equal to 0. Here k g of s h of s equal to minus 1. There is the g of s h of s indicate the open loop transfer function. So magnitude of the k g of s h of s equal to 1, and angle is angle of k g of s h of s, that equal to in bracket of 2n plus 1 into pi. Using open loop transfer function plus system parameter to analyze the closed loop system response, and its form k from 0 to infinite, and that draw on the S plot with the help of root locus. This is the basic that root locus segment are symmetrical above the real axis. Then k, that is equal to 1 upon g of s h of s, that k varies from 0 to infinite. If k equal to 0, that means g of s h of s equal to pole, and k tends to infinite, then g of s h of s equal to 0. You can find from that particular equation. This is the basic block or basic plot of S plane in sigma indicate real axis, j omega indicate imaginary axis. There is the different poles. If number of poles are moved, with the help of angle of asymptote, we can find the number of zeros to complete the root locus. So this is the angle equation. Now root locus construction. So first is loci branch. Each locus from poles k equal to 0 to zeros k tends to infinite. If n does not equal to n, for access zeros or poles, locus segment extend from infinity. Like if n minus m greater than 0, then n minus n branch tends to infinite. In other case, if n minus m tends less than 0, then m minus n branch infinite tends to 0. This is the real axis segment. Like if we have found some kind of location of poles and 0 like this, one pole, then 0, then poles, then we stand here. Then poles plus 0 is odd, then root locus is. If poles plus 0 is odd, then root loci is present. If you stand here after completion of this 0, then poles plus 0 is even, because 1 plus 1 is 2, so loci is not present. Similarly, you can check for different numbers of poles and asymptote angle. That can be found with the help of this theta. Theta, that is equal to 2k plus 1 into pi divided by n minus m, that k tends from 0, 1, 2. Then if n is equal to 6, m equal to 2, then theta is equal to 180 divided by 4. 6 minus 2 is 4, and that is equal to 45. So angle of asymptote is drawn with the help of centroid, and that angle made it 45 degree. Then centroid of the asymptote. So centroid of the asymptote find with the help of sigma of poles minus sigma of 0 divided by n minus m. That is number of, first you have to find the summation of number of poles, subtract number of 0, and then divide by number of poles by number of 0. Like example, g of h of s equal to 3s divided by s plus 2, s square plus 6s plus 18. In this case, 0 are 0. Then poles at minus 2, and you find the roots, then you get s equal to minus 3 plus j3, and the second is minus 3 j3. So what is the location of centroid? So sigma of poles, so minus 2 minus 3 plus j3 minus 3 minus j3 minus 0, 0 is 0, so 0. Divide by number of poles by number of zeros. The number of poles is, so number of poles are 3 and number of zeros are 1, so 3 minus 1, that is equal to 2. So when you found the solution, you get it -4. So -4 is the centroid location, and theta in this case is, from the previous equation, is 90. So -4 is centroid and asymptote is 90°. Then breakaway entry point. So in that case, you have to find a differentiation of the gain equation, and finally you get the solution with the help of root areas. So like this, in this case, kgh, k divided by s into s plus 1 into s plus 2. So 1 plus kgh, they are a characteristic function of the closed loop system. Then you put the equation in this particular 1 plus kgh, you get this particular kind of equation. Then you have to differentiate with, you find the k from this particular equation. Then you have to differentiate k with respect to s, and you get s equal to -0.423 and -1.1577. Next step is angle of departure and aperture. So angle of departure equation phi suffix d, that is equal to 180 plus angle of g into h, and acceptance angle, that is equal to 180 minus angle of g into h. Like example here, kgh, that is equal to k into s plus 2 divided by s plus 1 plus j into s plus 1 minus j. Angle of departure from the pole, that is equal to s equal to -1 minus j. Then you get the, you have to find the angle for the zeros minus angles of poles to get the angle of departure. If numbers of zeros are more compared to numbers of poles, you have to find the angle of aperture. So this is a solution or method to get the angle of departure. In this case, the angle of departure is 2 to 5. Next case, in this case, angle of aperture is fine because number of zeros are more compared to numbers of poles. So you will find the angle of aperture. Then the cross point of root locus and imaginary axis. So for that, you have to use root array. So this is the example of k divided by s into s plus 3, s square plus 2, s plus 2. The characteristic function of the closed systems are like s plus 3, s square plus 2, s plus 2 plus k equal to 0. Then you have to solve this. Finally, you have to put the, you have to find the solution with the help of root array. So s4, s2, 3, 2, 1, and 0. And similarly, you have to put the different value and get the. So this is the poles and zeros and dk by ds solution with the s1 and s2. And you, after solving this, all this particular mathematical term, you get the value of k equal to 12. And this is the plot for the particular given function. Here two poles are there, here three poles are there. So you find that 3 zeros at infinite, and for that here two poles are there. So one breakpoint is there. It goes the loci to find the zeros at particular angle. In this case, poles have to find the zeros in this particular direction. So this indicate the direction, and this is the cross point at j 4.5. Okay. Now the main task is example to be solved using scilab. So draw the root locus for the system. First, g of s h of s equal to 3s divided by s plus 2, s square plus 6s plus 18. Second is g of s h of s is equal to k by s, s plus 1, s plus 2 for k equal to 1. And third, g of s h of s that is equal to k divided by s, s plus 3, s square plus 2s plus 2 for k equal to 12. So all these three examples are from the presentation that we discussed earlier. So that we have to solve with the help of scilab. Okay, so now we move to the scilab and we try to find the root locus for the given. Find the root locus for the system g of s h of s equal to 3 into s divided by s plus 2, and second case multiplication s squared plus 6s plus 18. So that is the first example that we have to solve with the help of scilab. So first clear screen, then clear history, then timestamp from 0 to 15. semicolon to avoid the result on the screen. Sample of time from 0 to 15 in the range of 0.01. Then s equal to percentage s, that indicate for s polynomial. Then numerator equal to polynomial of now here 3s, so 0 3, that gives 3s. Then this is s for polynomial s, and then this is a coefficient kind of, so here coefficient. Okay, so it indicate 0 3 matrix generate as a numerator, yes, then s represent polynomial in s, coefficient represent coefficient of polynomial in s. Now for denominator, here we have find denominator in two way. Either we can find the single step, that s plus 2 multiply with this particular term, or we can separate s plus 2 and s square plus 6s plus 18, and then we can multiply the denominator and we get the final denominator. So we use second method. First we find the denominator 1, that is equal to polynomial minus 2. Here first is minus 2 roots, so with the help of roots method, so s and roots. Okay, here we here add semicolon to avoid the result on the screen. Then minus 2 matrix generate force of transfer function. Then similarly, s represent polynomial in s, and coefficient represent coefficient, and here roots are there. So here roots represent roots of the polynomial. Represent the roots of polynomial. Okay. Now similarly we have find the denominator 2 with the help of coefficient method. So okay, denominator 1, okay, then denominator 2, okay, so denominator 2 here poly, then now 18 plus 6s plus s squared, so 18 6s plus s squared, as here coefficient method, so you use coefficient. Okay, so 18 6 1 6 1 generate this matrix, generate s square plus 6s plus 18. Okay, then where s represent polynomial s and coefficient represent the coefficient of polynomial s. Now we have to multiply that's 2 denominator, so denominator equal to denominator 1 multiplied by denominator 2. Once again semicolon to avoid the result on the screen. Okay, so this is the final denominator of function Then we have find the system function that is equal to, with the help of system linear functions, linear, and for continuous, so C, and first we use numerator and then we use denominator. Okay, so here C for continuous. Now for root locus, one inbuilt function is there, that is evans. So evans function, and now you can scale as your like. Here I have used as 100, or this is a sufficient number to get the root locus on the screen to plot evans root locus of the given function. Okay, so first save this, then run this program. This is the result. So this is the evans root locus of the given system. You can see here. You can see there is no grid. So this is the real axis, this is imaginary axis, but you cannot find the grid on the location. So it will be difficult to find the value of different as an imaginary value. So here I have just put one called as grid. As grid. So draw as plane grid. Now run this program and you can see the result. So here zeros poles are also located. 0 with 3s, then poles, 3 poles are there that are indicated in with the cross sign. This is one button is there. If you click here, toggle data type model, and then you can find a different value on this particular evans root locus. Like if you click here, then you can see x equal to -2, y equal to 0. This is the pole location of s plus 2. Similarly, if you click here, so x 0, y 0, that means 0 at 3s equal to 0, so s equal to 0. Similarly, you can locate here. Then -3 plus 3j. So this is the another pole location. If I click here, then it gives the imaginary value location. So -3 minus 3 j, and this is a loop gain. So this kind of root locus is drawn. Here you can find the real axis, asymptotic direction, open loop poles, and this kind of notation is for the open loop 0. This is real axis, this is imaginary axis. Okay, this is the first one. Now for second one, I have just copied this code. Only small changes are required. So Control C. Now just okay, these are the things I have required. Okay, then second example is for finding g of s h of s equal to k into s, k divided by s. So k divided by s into s plus 1 into s plus 2 for k equal to 1. Okay, so here I have to define k equal to 1, or I can directly apply coefficient polynomial as a 1 in numerator. So this is same clear. See that. Okay, this is completely done. Not required. Numerator that is equal to polynomial. Now this is 1. I do not require this 2. So just okay. Numerator polynomial 0 here. Numerator's k value is 1 as coefficient 1 matrix generate a numerator as a 1, k equal to 1, as represent polynomial as, and coefficient represent the coefficient of polynomial in as. Then denominator is here roots are there, so poly 0 at 1 and at -1. So 0, -1 and -2 as and roots. So -0, -1, -2 matrix generate poles of the transfer function as represent polynomial as, and roots represent the roots of the polynomial. So I have not required this one because in single line I have completed this, so not required this line also. This is a final denominator. So and system function C numerator denominator, then evals and as grid. Okay, let's run this. First save this program and run this code. So this is the root locus of the particular second system function. 3 poles are there, so 3 cross are there. Then this is the loci indicate with the color. So this is the root locus, Evans root locus of the. So this is the Evans root locus of the second system function with 3 poles. Now 0. This is the real axis, the middle axis, asymptotic direction. This is the location of asymptotic poles only. So that's why only cross are there in the graph. Okay. Now we move to the third example. So in third example, we have to find root locus for the g of s, h of s equal to k divided by s plus 3, and in the second bracket s square plus 2s plus 2 for k equal to 12. So there is a I think I have to use the first one example. So just copy the first example. Okay, so this is done. Here as range as polynomial. Now numerator k equal to 12. So I use the first method that I've defined here, k that is equal to 12. Then polynomial, I just type k here, then as coefficient, then k matrix, generate the numerator as a 12, then as represent the polynomial as, coefficient represent coefficient of polynomial as, then in denominator first polynomial 0 and -3. So 0 and -3 as roots. So 0 -3 represent or generate poles of the transfer function at s equal to 0 and s equal to -3. S represent polynomial s, and roots represent roots of polynomial. Then final s square plus 2s plus 2. So polynomial s square, that means here s square plus 2s plus 2. S square plus 2s plus 2. Okay, so that is the way we can define s. Okay, so s square. I have to write in reverse way, like s first s square, 2s and 2. Okay, so now it is okay. S square plus 2s plus 2. As coefficient, it 2 to 1 that generate 2 to 1, that generate s square, then 2s, then plus 2. Then once again, s represent polynomial in s and coefficient represent coefficient of polynomial in s. Now I've used the denominator final as a multiplication of denominator 1 and denominator 2. So denominator 1 multiplied by denominator 2, there is a final denominator of given function. System function that equals system linear in C, numerator denominator, C for continuous, system linear indicate or generate the system linear function. Then Evans system function 100 to plot the Evans root locus of the given system, and S grid to draw as plane in grid. So let's first save this program and run this. This is the final one. So this is the Evans locus of the final system. You can see here 4 poles are there. There is no zero, so there is no zero in the particular Evans root locus, and also it is indicated in the plot that asymptotic direction with this particular line, and this indicate the open loop poles. This is the real axis and this is imaginary axis. You can try more number of example to find the Evans root locus of the any given system function. Hope you enjoyed the video. If any doubt or difficulty, you can comment on the particular section. If you like this video, you can also comment in the comment section box. Okay, thank you.